So in 1.5, our section's titled Exploring Angle Pairs, and that seems kind of like a general title, right? So what we're really going to be doing is this objective down beneath it, which is identifying some special pairs of angles, and then using those special pairs to find angle measures, much as we do with any kind of missing measurement in an algebra problem. So identify those angle pairs first. We start with what we call these adjacent angles pictured off to the side. So if we're looking at that description, we're looking for two coplanar, meaning just on the same surface, angles that have a common side. Like we have a common side between angle 1 and 2 here, common side between angle 1 and 3, or sorry, 3 and 4 there, a common vertex, and no common interior points that we say. So essentially, no common interior points means that they just don't overlap. So 3 and 4, two separate angles with no overlap except for that common side. And again, if I did have angles that overlap, that's not what we call adjacent. It's kind of like how we use adjacent in a common sense, just kind of mean next to each other. Vertical angles means that they're two angles whose sides are opposite rays. So for example, angle 1 and angle 2 here are what we call vertical angles, much like angle 3 and angle 4 up at the top and the bottom are vertical angles. Kind of would think these angles are just kind of across from each other at an intersection, 3 and 4, 1 and 2. And what we mean by those two angles whose sides are opposite rays, as let's say if I'm trying to form this side of angle 1, I can continue that and form the side of angle 2. If I'm trying to form this side of angle 1, I can continue that as an opposite ray and form the other side of angle 2. Complementary angles just means I can add up these two angles and get a sum of 90. These two complementary angles can either be non-adjacent, so just like 47 plus 43, add that to get together and I get 90, or they can be adjacent, so like angles 1 and angle 2 here are complementary because if I combine those, I get a right angle, which we also know is 90. Similar rule is supplementary, so it's common to get those two confused. Supplementary just means instead of a sum of 90, we have a sum of 180. So I actually just have one of those pictured here. But so, example, if I wanted to combine angle B with angle C, those two would be supplementary angles because now the sum is 180 rather than just 90. Or again, if they were adjacent, I'm going to find that they add up to form a straight angle just because it looks like if I add 3 and 4 together, I'm just going to get that to be 180 as well. So for the next figure, if I can resize that one, is going to be seeing if you guys can find pairs of these angles in that figure below. So yeah, let's see if I can resize that nice and good. So if I'm looking for angle BFD and angle CFD, again, if we want to tell if they're adjacent angles, first of all, again, picturing those angles, just how we draw them, we're going to name them. B going to F, continuing on to D would be this angle here. C, F, and then D would be that angle. Looks like it's almost kind of, I guess, inside of it right there. If I want to name them as adjacent angles, again, up to you, think if they are or not. Let's see those answers though. And the answer is no, again, because if I use CFD, the angle lies entirely within angle BFD, and we know that since there's no common interior points, if I have BFD and it just kind of overlaps that smaller angle CFD on the interior, we know that that's not going to count as adjacent. It's just going to be the angle contained within it. So not adjacent because they're not next to each other. If I look for angle AFB, again, if I'm picturing that, AFB, as I would name it, I would draw it. EFD, if I want a picture of those are vertical, I would say that they just about look vertical. Let's see if it's going to be true or not. And again, no, because if I'm trying to form my sides using opposite rays, I know it works for one of my sides, so FA as a ray and FD as a ray, I can continue with those two sides, but FE and FB are not opposite rays because I don't continue along the same line, so those are not what we call vertical angles. If I want to check if our last one is true, so AFE and BFC are complementary. Again, they don't necessarily have to be adjacent, so let's check that answer. They are complementary indeed, since if I add those two measures together, again, complementary just means a sum of 90. I don't need those to be stacked up next to each other as they are in that kind of right angle example. So add up the two and get 90. As long as they add up to 90, they don't have to be, again, what we call adjacent. So we have a brief rundown in this box of what we need, or sorry, what we can find rather, from just looking from a diagram. And again, this is specifically if the diagram is unmarked. If it's marked, of course, we're going to have a bunch of information, whatever they mark for us. But we can tell things are true in terms of angle pairs just by examining a figure in some cases. We can tell if angles are next to each other, which we call adjacent. We can tell if they're adjacent if they also add up to that straight line. So combine them and I make a straight line. That's what we also call supplementary. We can tell if angles are vertical angles because we can just continue those opposite rays. But what I can't tell is I can't tell if they're congruent by looking at them. And even if they look like they're the same angle measurement, I need to be sure by measuring that. I can't tell if it's a right angle for the same reason. I can't just guess. I need to know if it's marked, if it's a right angle, or if I know that it's exactly 90, it's a right angle. Otherwise, I can't tell if it looks close to a right angle or not. And for the same reason, if I can't tell if something's a right angle, I'm also not going to be able to tell if they add up to 90 degrees, so I can't tell if they're complementary. So there's a few things we can conclude from this figure. Again, I would recommend pausing it and try and see if you can come up with as many as you can. I'm just going to reveal them piece by piece. It looks like the first thing we can reveal is that 1 and 2. Again, we said that we can't say that angles are congruent, but in this case they are marked. This is really the one marking we have in our figure with those 2 arc markings for congruency. So you still want to use congruency markings whenever possible. In this case, 1 and 2 are the only ones marked congruent. We can also tell a few other things. We can tell that 3 and 5 are vertical angles. Again, if I was to combine those angle pairs together, it looks like I'm continuing those opposite rays. Didn't draw that very well, but yeah, those are vertical. Notice that angle 1 and angle 4, though, for example, are not quite going to be vertical. I think this line is going to continue kind of through 4, so that's not going to work. But instead, I have a few adjacent pairs. So again, we can describe something like 1 and 2, and I kind of have the description down beneath it. So let's just reveal all of them. Adjacent angle pairs, again, being 1 and 2 can be adjacent, 2 and 3 can be adjacent, 3 and 4 can be adjacent, 4 and 5. There's a bunch of angle pairs next to each other that are adjacent. Again, basically anything that's next to another angle by using that same common side, that would be an adjacent angle pair. And specifically, adjacent and supplementary would be a couple of these. 3 and 4 are adjacent and they combine to make that straight line continues, that goes from 3 to 4. And I do have another pair, if it looks like I combine 4 and 5, those are adjacent angles that also add up to form my straight line continuing on this way. That would also be an adjacent pair that's supplementary as well. So again, just a little bit more specific information we can give about those two. To try that again, to figure out if we can draw any conclusions from a diagram. In this case, kind of like with our previous example, we do have, it looks like, a couple congruency markings. And in that case, again, as you're going piece by piece, you want to just make kind of a yes or no conclusion if these things would necessarily be true. With our first one, because of that congruency marking, we know that's true. Again, that's the whole reason those markings are there. TW and WV as those two segments. Those are used to mark segment congruency, whether that's a length of, like, let's say 5 and 5, 10 and 10, 100 and 100, not going to matter. Just need to know that they're congruent with those markings. If I want to know if PW is congruent to WQ, again, you can try to give your best guess on that one, but we actually don't have evidence for it, even though it looks like it may be true. I would need markings on these two segments, again, PW and WQ. So this is an example of using the case that we can't just estimate. Even if they look like they're about the same length, I would need those markings in order to tell if they're congruent. If I don't have those markings, again, I can't tell if they're congruent or not. So if I want to figure out if TWQ is a right angle, might have seen that example from before with our box up there, but yeah, no, there's not a way to tell if that's a right angle without a marking, because even if it looks like a right angle, we would need that little square box in the corner to indicate that that's a right angle. If not, this could be slightly under 90 degrees or slightly greater than 90 degrees, and we're not really sure just based on looking on the diagram. Again, looks like it's a right angle, but we don't know for sure. Last one, we're asking if TV bisects PQ. Need to know again what a bisector means in this case for a segment, but no, we don't have evidence for that. Much of the same reason for our second answer. We don't know if PW and WQ are congruent segments, so for this segment to be bisected, I would need to have those congruency markings there. I actually do know that PQ bisects this segment from TV because we do have that congruency. It is split in half between those two pieces, but I can't say it the other way around. Again, for TV to act as the bisector, that's the segment that's doing the cutting. TV is cutting PQ in half. In this case, again, we would need the markings for. I could reverse that, and in that case, we do have the evidence. PQ does bisect segment TV because, again, we have the congruency marking TW and WV as congruent segments. A couple other vocab terms. Linear pair is a pair of adjacent angles whose non-common sides are opposite rays. I've actually seen this before. We just call this like two things at the same time. These are your pairs that are adjacent to each other and they're supplementary, so they add up to form what we call that straight angle. Again, straight angle essentially just being your straight line. So we would call, for example, angle ABD and angle DBC my linear pair in this case because, again, that is my pair that's adjacent and supplementary. So we have our rule. I was kind of actually going ahead on myself a little bit. Two angles form a linear pair. Again, that's why we know that they are supplementary, because they just add up to form that straight angle. Straight angle is 180, and angles that are supplementary, again, also add up to 180. So that's how we know that they're going to add up to form that straight line. And if I use that fact, I can use that to solve questions with some algebraic expressions. I know that if these two angles form a linear pair, and we're given expressions for both, that means if I'm to add, let's say, the left-hand side and the right-hand side, I know that 2x plus 24 for angle KPL, it looks like the measure there. If I add the measure next to it, 4x plus 36, I know that since those add up to form a linear pair, that's my proof that, again, they're supplementary. So in general, I wouldn't know if they would be equal to a certain value. In this case, I know that since they're supplementary, they're going to equal 180. And now I'm just solving this problem algebraically to try and get my solution for x. So again, if I combine like terms, 6x plus 60 is going to be equal to 180. If I keep solving, I can subtract 60 from both sides. I can divide by 6 to get my answer for x. Much as we do in a lot of other algebra questions, we want to make sure we're actually solving for the measures of the angles and not just for our variable. So if I substitute back in, again, for example, in each expression, I know that 2 times 20 plus 24 is the measure of KPL. That's going to be 40 plus 24. Whoops, not 60. Getting ahead of myself. That's going to be 64 degrees, it looks like, for KPL. And again, you can always use a shortcut to find the one that's next to it. We know that they add up to 180. So I could substitute into this next expression, or I could take 180 degrees, subtract the one that we've already found, and that's a way to show it my next measurement is going to be 116 degrees. Again, should add up to 180 and should also work if I substitute 20 back into this expression. I should get my 116. A little interruption in the video there, but next term is going to be an angle bisector. We've seen segment bisectors before. If you remember what that means, it means that I have just any kind of ray, line, or line segment that cuts a segment rather into two congruent pieces. So essentially an angle bisector is going to be the same thing, just now working with an angle rather than working with a segment. So if we have an angle, in this case we have angle XAZ or ZAX, either way, an angle bisector is going to be something like this ray AY that cuts this angle in half in a way that, let's say if this is like 10 degrees and 10 degrees, it's splitting that into two congruent angles. Again, just like we split our segment in a segment bisector into two congruent segments with two of them the same length, we're going to split our angle into two congruent angles, both of them having the same measure. And we can use segment bisectors, or angle bisectors rather, if we're looking to solve algebraic questions, much like these next two. Our first one's saying that if ray AC bisects this angle DAB, if we know that the measure of angle DAC, which is marked, is 58 degrees, we're looking for the measure of angle DAB, which we also want to be careful, not looking for this measurement right here. That would be the measurement of CAB. If I'm looking for DAB, it looks like what we're actually looking for is the largest angle of those three that share A as a vertex. So if I know that 58 degrees is going to be the measure of DAC, we also know that the other one next to it, so that would be angle CAB, that's 58 degrees as well, again by the definition of that angle bisector. And since that's been cut in half with those two congruent angles, all I got to do to find the largest angle there is I could either do 58 plus 58. I think the easiest often is just to double it, so 58 times 2. That's going to be the measurement of the largest angle there. We can use our notation to say the measure of angle DAC is looking for DAB, is 116. Again, just by doubling that small one that we found, or just by thinking, take 58 and add another 58 next to it, that's going to give us that 116. I would say in any kind of question that starts this next way, where I have a bisector that's not drawn, you can always just draw yourself a little sketch. So if I have this angle that's described as JKL, and I need a bisector for that as ray KM, so ray KM cutting through the middle-ish, something like this. We know this time kind of the opposite starting situation that we had before. Last time we knew one of those smaller angles and we had to double it to find the larger measurement. Here we're kind of going the other way around. Here you know the measurement all the way from JKL. Again, that largest angle it looks like is going to be a measure of 72 degrees. And we want to use that fact to figure out the measure of JKM, which it looks like is just this little portion right here. Let's do that in a different color. Looking for the measurement of JKM, which is just that angle. So now we're just working backwards from that last question. This time, if I know the entire angle is 72 degrees, I'm splitting that into two congruent angles to form those two smaller ones on the interior, one of them being the angle that we're looking for. So if I take that biggest angle and split it evenly into two, I get that both of those angles should be 36 degrees in order for that to be a bisector. So again, just using our fancy notation, the measure of angle JKM just be 36. Again, kind of just the reverse of that previous question. We just want to make sure that we know if I start with the smallest measure, I can double it. That gives me the bigger angle, or I can work my way backwards as we did on that last question. If I start with the biggest total, I can divide that into two even parts, and that's going to be the measure of my smaller angle.